What's up, people? Welcome back to the Ephemeris Podcast. I am your host, Aphelion, and Ephemeris Podcast is a weekly astronomy podcast where we are currently getting into recent developments in terms of the world of astronomy. So that's a quick rundown on what we're here for. If you are a regular viewer of the channel, then you know we get into 3 articles every week. Just discussing some new stuff in the universe that we have discovered. So let's get straight into it. The first article we have today is going to be about the first strong evidence of neutrinos in astrophysics, or its first observation, really, in full form. Then we have the photoevaporation in the Orion Nebula to follow that up, and lastly we will talk about a new supercluster that has been discovered in the cosmos. So our first story: neutrinos, neutron stars, all that good stuff, supernova remnants. Let's get right into it. So our first story concerns a supernova remnant named SN 1970 or 1987A, and 1987 being the year that the supernova actually happened. Which is pretty self-explanatory. Before we even talk about what the revelation is with this supernova remnant we have, there are some bizarre attributes that we can discuss. At its core, no pun intended, supernova 1987A is a type 2 supernova, so it's a core collapse supernova, and it's in the Large Magellanic Cloud. The fact that it's in the LMC, for short, means that in the grand scheme of things, it's quite close. I believe it's 160,000 light years, which might sound like very, very distant, but when thinking about the scale of the universe, a bit short. And the progenitor of this supernova that happened in 1987 was a blue supergiant, which is surprising. Let's put it that way. On first thought, there's nothing to be surprised about, because you'd think a large star would obviously be the cause for a core collapse supernova anyway. But when you think about it again, why is a blue star transitioning immediately into a supernova? That's not really supposed to happen. So this is definitely a rare occurrence. There's speculation that attributes the progenitor's blue color to its chemical composition rather than the stage of its life cycle. So it's just because it's blue doesn't mean it's really early on in its life cycle. It might just be that lack of certain elements make it look blue, but it has been through quite a few phases of its life cycle. So yeah, it's possible, but definitely rare, and perhaps some would say unlikely. So this supernova already, for what it is quite unusual. But another detail to add on here is that up until a certain point, we weren't able to find a stellar remnant for this supernova. And we'd actually detected neutrinos from the supernova event, which would indicate that a neutron star had formed, but we couldn't see it. And yeah, this is actually the first time that neutrinos were detected from a supernova event, which is why, I mentioned more of a first observation of them in the world of astrophysics, because that was the case. So, because we did not see the neutron star that was supposed to be there, a lot of theories flew around. Some thought it was obscured. Some thought that the neutron star was an extreme pulsar, either less magnetic or too magnetic, or very highly magnetic. And there were other theories that said that the star further collapsed into a black hole, which is quite absurd. But even more absurd than that would be the possibility of a quark star, which has been a theoretical star for the most part. But what a quark star would be is essentially, instead of a star being held together by neutron or electron degeneracy pressure, you'd have a star supported by quarks. So lots of theories around this neutron star that hadn't showed up, but then with the release of a new study, we actually found the neutron star, or very strong evidence to support that it's there. So astronomers basically had evidence piling up for several years, starting from, I believe, like 2019. But in 2024, astronomers found the final evidence that was needed to confirm its existence. So the data was taken from James Webb Space Telescope, MIRI, and near infrared spec data. And so that showed us emission lines of ionized argon within the central region, and it also showed us ionized sulfur that was detected in the vicinity. So the only plausible cause for these ionized particles or elements would have been heavy X-ray and ultraviolet radiation, which would have to come from a neutron star. If not, then it would have to come from a pulsar wind nebula, but nonetheless, there had to be some kind of neutron star in the system. So, yeah, there's that. That's some really, really good evidence to show that there has to be something in there. There can't just be nothing, or some of these wild theories about quark stars and black holes. But there's still reason to believe that what these scientists have discovered isn't conclusive, and that's what a co-author of the study explains. His name is Mike Barlow. He says, quote, "Our detection with James Webb's MIRI and near spectrometers of strong ionized argon and sulfur emission lines from the very center of the nebula that surrounds supernova 1987A is direct evidence of the presence of a central source of ionizing radiation. Our data can only be fitted with a neutron star as the power source of that ionizing radiation. We now know that there is a compact source of ionizing radiation, most likely by a neutron star. We have been looking for this from the time of the explosion, but had to wait for James Webb Space Telescope to be able to verify the predictions." So a slight level of uncertainty with just flat out saying that it's a neutron star. Obviously, it's kind of like saying, oh, well, there's a 1% uncertainty. It's not very significant, but I think it should be said that to a certain level, it's not conclusive. We can't say like, oh, we've visually detected this neutron star, but the evidence is piling up to support that it's there. So yeah, that's the point I wanted to make. It might seem a little bit unclear, so I just wanted to clarify that. I'd also like to mention something that our article quickly discusses, which is a really interesting idea, at least in my opinion. It says that 99.9% of the energy emitted by the supernova remnant was released as neutrinos, which, I mean, tells you about the nature of quantum physics when you zoom things out, right? To imagine that such a small quantum particle, trillions of which might pass through your body every second, constitutes most of the energy of some of the largest explosions in the universe, it's something. So, yeah, I thought it was really cool to mention that. And before I end this story, there's also another mystery to uncover with supernova 1987A, which I'm just going to quickly talk about here. Perhaps we could come back to it and in a different episode. But the supernova remnant, it's got a ring of clumps of glowing hydrogen plasma, and we haven't been able to fully explain why they've occurred. Scientists are working on this issue to complete the theory for why this would occur by using what is known as Crow's instability, which typically has to do with aerodynamics. A quote from a different article, one separate from the one we just discussed. It states, quote, "Scientists do theorize, however, that a ring of gas surrounding the star that exploded to create supernova 1987A was created by the merger of two stars. This collision would have ripped hydrogen away from the two stars, with the element escaping into space as the merger spurred a blue supergiant star." So a little bit before the supernova remnant, but still some of the causation for this other phenomenon that's occurred in the supernova remnant. So, yeah, that's what we've got for this very, very unusual SN 1987A. Our next story is, as we mentioned before, about ultraviolet winds and photo evaporation that's occurring to a young star and its protoplanetary disk, specifically in the Orion Nebula. So, the Orion Nebula doesn't need much of an introduction. Most people who have at least gotten like a surface level understanding of sort of celestial objects will know Orion Nebula. It's a diffuse nebula. It's about 2,000 solar masses, so 2,000 times the mass of the sun, and it's 24 light years across. And it's quite a spectacle to see if you look up an image, if you actually observe the nebula. I believe you can. I don't know if you can see it with a naked eye. I don't know if it's this one or a different celestial object that I was researching this week that you could see with a naked eye, but Orion Nebula might be one of them. So yeah, it's quite a nice nebula to observe. Lots of star formation is to be expected in nebulas like the Orion Nebula, which is also known as M42. There's a lot of regions of dust and gas, and you might find a protostar with a protoplanetary disk somewhere in there. If you didn't, it'd be very unusual. What you might not expect, though, is to see radiation that is so strong in this nebula that it disintegrates the protoplanetary disk of some of these young stars. And that's what we've got here. That's the premise of our second story. A quote from the article sums up this issue quite well. Using near-infrared and sub-millimeter measurements from the JWST and the Atacama Large Millimeter Array, respectively, Olivier Bernet, hopefully I'm saying that correctly, and colleagues report observations of an FUV, or far UV, irradiated protoplanetary disk, D203506, located inside the Orion Nebula. By modeling the kinematics and excitation of the emission lines detected within the photodissociation region, the researchers found that D203506 is losing mass at a high rate due to far UV-driven heating and ionization. So, face value, that's not going to make any sense because we have not talked about any of the themes that have been brought up in this statement. So, let's do some explaining. There's a process that limits the accretion disk of a protostar, and that's called photoevaporation. So this happens when the upper layers of protoplanetary disks are heated by X-ray or ultraviolet protons, which increases the gas temperature and causes it to escape from the system. So if there's a mechanism that creates borders essentially for a protoplanetary disk, it's this process called photoevaporation that just like doesn't allow gas to exist too far out from its star because of the X-ray and ultraviolet exposure. So this process usually occurs when a protostar is close to other massive stars with X-ray or UV radiation, and it allows us to define a so-called photodissociation region. So what was done in this scenario by a group of astronomers was by modeling what was going on in the photodissociation region, or the PDR, of protostars and of this specific protostar and its disk. They found that there was a high rate of photoevaporation. How much photoevaporation? Well, 1 Earth mass worth of material per year, which is really fast. That's a really fast rate of loss because perhaps let's take it from the perspective of our sun. Our sun managed to form all of the planets plus planetesimals with its mass, or with the protoplanetary disk's mass. So if you're losing an Earth mass a year, you're taking a lot away from a protostar's ability to create planets like the sun or even like Jupiter, which is like, I believe, 1,300 times the mass of the Earth. So yeah, the fact that in a year, which is a very, very short time scale for the universe, you're just losing an Earth's worth of mass, that's very significant. The entire disk only has 10 Jupiter masses worth of material, which means the disk might be gone in only 1,000,000 years, which again is quite short for the timescale of the universe. So, really, this could be one of many instances where the universe is losing out on future exoplanets. I mean, it is Orion Nebula, which is quite far away, but we're all obviously on the mission as a society to find as many exoplanets as we can based on, where most astronomy researchers are devoting their energy to. At least I think that's the case. And a quote from the article that talks about this idea states, quote, "In order to improve and expand this understanding, Byrne and colleagues have been granted further time on JWST to build a catalog of similar protoplanetary disks in the Orion Nebula. Astronomers would then be able to map the fates of similar stars and help create and develop models that could be applied to other star-forming clusters as well." So they're being given time to look at different places where this might be happening, and if we find that, then we know there's some real potential that's being lost out there in the universe. But yeah, I don't mean to be a sort of like a buzzkill, but because the stories have been quite optimistic for the most part. But I mean, it's just a one occurrence that might lead to many others and many other discoveries that might lead us into the idea that I just mentioned. So anyways, that is our second story. It's now time to move on to the last story, and I believe I've saved the best for last here because we're going to talk about something gigantic. Again, I know. It's been a theme for this season pretty much, and we're back to it again. And I cannot stop myself from looking into big numbers and large numbers. So we're talking about superclusters. And to understand what superclusters are and how they compare to everything else in the universe, we've got to familiarize ourselves with the hierarchy of the universe, I guess you could call it. So at the bottom of the hierarchy, perhaps you would put interstellar matter like gas and dust, which is not formed into any sort of stellar object like a planet or a star. Nothing of that sort, just material that you need to make it. We could put that at the bottom of the hierarchy, if that's what we're going to call it. So let's start out there. We've got gas and dust, interstellar matter. From there, if you want to move higher up the ladder here, you'd go to planets, which are remnants of protostars in a way because they form from protoplanetary disks, and we've talked about that a little bit already. So above planets would be stars, and these are huge balls of gas. It might be convenient to put some stellar remnants and star-like structures here as well, like white dwarfs and planetary nebula and supernova remnants and pulsars and stellar mass black holes. They're like, the masses and size vary, but I think they can all be grouped into one category as it won't really fit in anywhere else. So going further than that, you would have star clusters and galaxies, which are all around more organized groups of stars, and you might include like supermassive black holes in this category because they tend to be at the center of galaxies and all that. But for now, let's just simplify this category to galaxies because it's just easier to digest. We don't have to think about all the nuances. So above galaxies in the hierarchy of the universe, there are galaxy clusters, like the Virgo cluster, which is quite close to us. I believe, I don't remember which cluster we specifically are in, but I remember that we're in the local galaxy group, which is actually the next part of our hierarchy. Above galaxy clusters, you'd have superclusters and galaxy groups. If okay, I think I've got that correct. Yeah. Okay. So yeah, above galaxy clusters, you'd have galaxy groups, and superclusters. And so this tier is the ultimate one at the hierarchy of the universe. It's a conglomerate of galaxy clusters. And so beyond being near the Virgo cluster, we might consider ourselves a part of the Virgo supercluster. So just an application of this whole hierarchical idea here. Hopefully that's registered well. So you got interstellar matter, planets, stars, star clusters and galaxies, galaxy clusters, galaxy groups, and superclusters. So superclusters are pretty much the hugest groups of stellar objects that you can get. And the collection of superclusters is what makes up the entire observable universe. There are quite a few superclusters that we know of, and the furthest ones are the ones that I believe make the edge of the observable universe for us. So that begs the question, okay, we've organized the many galaxies in the observable universe into galaxy clusters and superclusters, and they make up our understanding of the observable universe. But what happens when we discover a new supercluster? Does that expand how much we see? Like, what's going on there? The answer to that question is actually quite spectacular. And it's what we're going to discuss with this last article that we have here. Astronomers have recently discovered up to 662 new superclusters in the universe, and have found one in particular that will fit in perfectly to the nature of this podcast, as I talked about. Astronomers have discovered what is now named as the Einasto supercluster, named in honor of Estonian astrophysicist Jan Einasto. Hopefully I'm saying that name correctly. And he was one of the discoverers of the large-scale structure of the universe. So, Einasto supercluster. Its size and mass... Actually, what's a good way of putting it? I'm running out of words here. So, its size and mass... Let's just put it this way. Are astronomical among even the astronomical. Alright? Because the Einasto supercluster has the mass of 26 quadrillion suns. Okay, now if you think I'm going to find an equivalent to 26 quadrillion suns, you'd be dead wrong. Except I just lied. I have to do it, right? So, everybody knows Avogadro's number. 6.02 times 10 to the 23rd power. 26 quadrillion suns is about 10 to the power of 22 Earths. So if you consider the Earth to be a single molecule, if you scale it down to a single molecule, then the Einasto supercluster is a whole mole of that molecule. One molecule compared to 22.4 liters of that same molecule. It just seems impossible. And even better, the article makes its own comparison. In terms of mass, if the sun were the same mass as a golf ball, one of these superclusters would have the same mass as Mount Everest. Like, imagine putting a golf ball at the base of Mount Everest and then zooming out and looking at Mount Everest. And then you label that golf ball as the sun and this supercluster is Mount Everest. It's just, I don't know. There's a reason why I love bringing this stuff up on the podcast, and I don't think I'll stop doing it. But that's not even the end of the story, by the way. The supercluster is so vast that it would take a light signal 360 million years to get from one end to the other. So don't even think about trying to travel through the supercluster. You just won't be able to. You'll pass away before you even get like 1% of the way through. And I mean, again, this is just not a number to sneeze at, because let's put it this way. The highest possible isophotal diameter of the Milky Way is close to 90,000 light years. So this supercluster, in a way, is essentially 4,000 Milky Ways across. which is insane. I think the comparison that was brought up in the article is like, if you took a coin and put it at the corner of a football pitch, right? Basically, that quarter would be the equivalent of, is the diameter of the sun or the earth, something like that. But I mean, it's just these superclusters is just huge, and the average supercluster doesn't even rank far below these numbers. So like 200,000 light years across and 6 quadrillion suns on average, which is still extremely crazy. Now, the Ionosto supercluster is also 3 billion light years away. If you want to try and imagine what 3 billion light years might be like, here you go. If you stack 1 billion $1 bills, the stack's height is about like 67.9 miles into the sky, or around like 360,000 feet, right? You multiply that by 3, you get just above 1 million feet, or 300,000 meters, not even feet, but meters, which, if you start from the ground up, will get you to the thermosphere of the Earth, which is already extremely high. Like, planes fly like 10,000 times, or 10 times less high than that. So, now, that's already super high, but you have to consider that the height of a single dollar bill is 0.0043 inches. So if you replace the height of a single dollar bill with the distance of a light year, right? Because we've got 3 billion single dollar bills and we're looking for 3 billion light years, right? If you change that height of a single dollar bill with the distance of a light year, you scale 300,000 meters up by 100 million. I have no words. It's just I'm speechless. Like 100 million. What does that even mean? And that's the amount that you have to scale up this number by to even think about what 3 billion light years is like. It's astounding. And I'm genuinely going to run out of words for how I describe these large numbers. Like one day I'm actually going to give up, but until then, I mean, like, I have no words. Again, I have no words. So here, let's not get too carried away. We're talking about supercluster. Ionosto supercluster. That's what we're talking about. Okay, here we go. These superclusters, besides the numbers, are interesting to us because they tell us about gravitational effects of a supercluster's density on the mass within it. These things are so huge on the astronomical scale that we can observe macrogravity, in a sense, because sort of observing the effects of the expansion of the universe and sort of how gravitational masses affect its expansion and how it interacts with itself is like, you can only observe it when you're looking at huge objects like superclusters. And so seeing these new superclusters, which are about 662 of them, that gives us a lot of information on sort of, I guess, macro gravitational effects, if that's what you want to call it. And more superclusters means more places to observe the effects of dark energy, given the same line of reasoning, right? A quote from the article that sort of nails this point down says, quote, "The team behind these findings observed that galaxies in these superclusters appear to be separating at lower expansion speeds than expected. The scientists believe dark energy may eventually overwhelm the gravitational attraction between galaxies in a supercluster, so studying these systems could help answer questions about troubling discrepancies observed in the universe's rate of expansion." So we've talked a lot about this, like, why do we need dark matter? Why do we need dark energy? Are we actually seeing what we expect? And so this is just sort of another thing to look at when we're thinking about all that kind of stuff. So yeah, that's all I've got for superclusters. The numbers are just, again, they leave me quite speechless at the end. because not only do I have to be stunned by seeing the number in an article, I also have to go through and really find numbers that will help digest how huge some of these values are. So, anyways, that's enough of me talking about big numbers, and that's the end of the episode. If you all enjoyed listening to these news stories in the world of astronomy, I would sincerely appreciate a follow on Spotify if that's where you're listening, and a subscribe on YouTube if you're listening there, and if you're on YouTube, for returning viewers, I'd sincerely appreciate if you all made sure that you're getting all of the notifications for these uploads, because again, YouTube is not good at recommending my content to returning viewers. So yeah, that's all I've got to say, and until the next episode, I will see you all later. Peace.